Thank you. Thank you, Olivier. Thank you, all the organizers, especially Rafal, Hermine, Philippe. It's always a privilege to be in a mathematical monastery like Lumini. And each time I have the opportunity to come, I accept, even though I feel like I shouldn't. Because I'm not a mathematician anymore. I work in a statistics department. So anyways, this is the most important slide. This is joint work with a brilliant guy, Jingqi Shen, who now works for Airbnb. So you're in safe hands, you know. He's a brilliant, truly brilliant guy. And Tailan Xing, who inspired us all, to, and of course is an integral part of this work, to work on functional stuff. So there are two papers. Basically, one is published, and the other one is a little longer with a supplement on Matheron theory. If you want to look at the details, you can find them there. And we were funded by the NSF. So I just wanted to, this is the second most important slide, mention Marvin Mershard, who's a good friend of mine and collaborator, and to say a few things that maybe will have come unnoticed. He's actually the guy behind regular variation for measures. And he in his dissertation in 1984 worked with the M0 topology, and later on, you know, maybe a suboptimal topology was used and so on. Well, of course, he didn't realize that this extends to infinite dimensional spaces and so on. He did a lot of work on operator stability, operator self-similarity, fractional calculus. Hermine knows him better than me. Always smiling and supportive, amazing guy. And I know it's taking time, but you know, I want to mention what sort of he mentioned a long time ago. Life is but a string of days. Make sure that every day you find time to work on something you enjoy. Otherwise, you will not enjoy life. Simple. True. So here's I'll start with the big picture. Here's the outline of my talk. We'll talk about intrinsic stationarity, which is essentially stationary increments of higher order. And it was introduced by Matheron. This talk, by the way, introduces a lot, sort of a new language maybe to many of you, which is unfortunate, to say simple things, okay? So please forgive me and just take this notation with a grain of salt. What started this project is an attempt to extend Falconer's theorem, and I'll state it more carefully, a series of Falconer's theorems on tangent fields. Then sort of this work on Falconer's theorems, which happened to extend to processes taking values in a Hilbert space, forced us to definitely take a closer look at the spectral theory of these intrinsic random functions, which are basically stochastic processes with stationary increments, that take values in a Hilbert space. And this is all sort of motivated by work that Tailan is very well known for. This is functional data analysis in statistics, where basically the formalism is that your observations are functions. Of course, they never really are, never truly function through entire functions are observed. They're sampled and so on. But many interesting probabilistic aspects, statistical aspects remain in this theory. Then we'll take a break from this abstraction, and we'll talk about variograms in infinite divisible laws. I'm sure I'm reinventing the wheel, and things like this were known to geniuses like Schoenberg 90 years ago. And then I'll return, hopefully if time permits, and talk about self-similar Hilbert space-valued intrinsic random functions, where we could say something more. Again, everything is, there's no heavy tails here. This is based on the spectral theory. And by saying spectral, I mean second-order processes, processes whose second moments exist. All right, so the big picture. So what's the main theme of this? Function-valued stochastic processes. So stochastic process X indexed by RD. Okay, it will be interesting if it's indexed by sphere or manifold and so on. But we are interested in a process indexed by RD, whose values are elements in a separable Hilbert space H. That's it. That's the main theme. So our goal is to characterize their local behavior by studying something what's known as a tangent process. Namely, okay, so here I'm recalling the classical definition of a tangent process. You look at a little increment around time t0. okay, x of r times t plus t naught minus x of t naught. And r is going to be sent to 0. So this difference, if you have stochastically continuous process, will go to 0. So you need to divide by something small, AR going to 0, to get some non-trivial limit. But if, lo and behold, if you can find such an AR such that you have a non-trivial limit, the limit is called a tangent field at t0. Okay. So we will end up defining higher order tangent processes. In other words, instead of this first order increment, we will look at higher order increments. And of course, this can get very ugly because, you know, higher order increments, you know, but how, what is the step size, and so on. So that's why there is a need for this heavy notation. Matheron found a way to deal with this in the framework of intrinsic random functions called IRFs. Okay. So we'll happen to, I mean, we will need to extend the theory a little bit of Matheron to be able to talk about Hilbert space valued process. Remember, the main theme is our process will take values in the Hilbert space. So most naturally, because these tangent fields will end up being self-similar. Well, take a limit in probability, you get something that is in some sense invariant to some action. There's going to be self-similarity. The tangent fields are self-similar. So we will end up studying self-similar, maybe operator self-similar processes. So I claim that we provide somewhat unifying framework and so on. So let me just finish the big picture again. So what does the spectral theory entail? Well, to recall the famous Bochner theorem, so if you have a function phi assigning a complex number to every point in a Euclidean space Rd, I mean, if it's positive definite, if given that it's continuous at 0, it's positive definite if and only if there exists a finite measure mu such that phi is its Fourier transform. Okay? So Bochner's theorem has been extended and generalized in ways I don't understand. But let's think about the simple ways that we might encounter in practice. I mean, of course, autocovariance functions are positive definite, and you know, assuming you're dealing with a stochastically continuous process, okay, they're really characterized through Bochner's theorem. So this is bread and butter. But what happens if your process takes vector values, okay, or even values in an infinite dimensional Hilbert space H? Okay? So, of course, then the natural object is the cross-covariance function, which now one can think of it as a matrix, as sort of infinite dimensional matrix, okay, indexed by the time lag t minus s. But it really is actually a trace class operator. Okay, we'll define this is a trace class operator from the Hilbert space H to the Hilbert space H. But the way I want to think about it is basically a matrix. So then, of course, Bochner's theorem extends, but it requires a bit of work. And then in this case, the measure mu that you have to take, okay, will have to be operator valued. That's all. It will have to take values in the space of positive trace class operators. So this actually has been done by Neeb and all that, but we reproved it just for building our self-confidence. Okay, so keep going. All right. A little bit more from the big picture. So what happens next if x is not stationary but has stationary increments? Now, of course, this has been looked at extensively. Variograms have been characterized as early as Schoenberg. So Schoenberg and Bochner were sort of chasing each other, proving fundamental theorem after fundamental theorem. Turns out that Gelfand and Vilenkin have like these 4 volumes, wonderful volumes, which I highly recommend. They're very accessible to read, written in the 60s. So one of their volumes develops a theory of stochastic processes taking values in a space of generalized functions. And they developed pretty completely the second order theory, also theory of processes with higher order stationary increments. The only downside a little bit was that they worked with stochastic processes that take values in the space of generalized functions and didn't care about applications necessarily. But these are harder to wrap your head around. So Matheron, in a sense, developed a useful theory which somewhat, one can argue that specializes it, but basically it applies to classic processes. That's pretty much my understanding of it, which is bread and butter in spatial statistics. So he developed the language for intrinsic random functions that can handle processes with stationary increments of higher order. So we consider this in our paper. So let me talk about intrinsic stationarity, or at least the way I understand it. Please interrupt me if you have corrections, any point of time, questions, corrections especially. So I asked myself, I was wondering how to present this talk, and so this is one of my motivating slides. What if we want to develop a notion of stationarity that's stationarity modulo trends? And this maybe happens in geostatistics somewhere. Sort of you shift somewhere else in space, and the random phenomena should not change up to a trend. Okay? So we want to say that a stochastic process X, let's say we're dealing with a scalar-valued stochastic process, indexed by RD, is stationary model a class of functions F if, when you shift the process by a vector h in time and space, then the resulting stochastic process is equal in distribution to the original one plus potentially some random trend. Okay, I'm not saying that F is deterministic. It could be random. X and F here on the right-hand side could be dependent. I don't know. But F, this F in blue, has to belong to this fixed set of trends. Okay. And it's natural to require these trends to be a space of functions that are closed in the translations and so on. So this is what people call F stationarity. Okay. So, well, but how to really understand that? Okay. So it's a bit cumbersome. Indexing X by time or space by t and just dragging a trend function is a bit cumbersome. But instead, if you view the stochastic process as indexed by some sort of test functions that kill the trend, things simplify tremendously. Okay. So in other words, I want to deal with this phenomenon of intrinsic stationarity by basically viewing my process X modulo any kind of trend. So it's kind of like an equivalence class. Okay. So this kind of motivates the language of allowable linear combinations or these signed measures that Matheron introduced in the 70s. So consider the following types of, he calls them signed measures, like measures that can take plus or minus sign. But they're basically measures concentrated on finite number of atoms, T1 through Tn. And at each atom, at each location, Tj, they put a charge, which can, in this case, we can take it at any complex number, Cj. Okay? So why are they measures? Basically, notationally, they behave like measures, basically. So we will write x of lambda for the integral of x of t lambda dt. And this integral is just a glorified sum of Cj x of Tj. And these lambdas are pretty much arbitrary. So choose your Tj's, choose your Cj's, you get the lambda, and so on. Certainly, the law of the stochastic process X is characterized by the finite dimensional distributions of this X of lambda. Now, how are we going to kill trends? So let lambda f, which is a subset of these measures, be the set of measures that kill all these polynomials. Not polynomials, but f's. Okay, you'll see why polynomials appear in a second. But so all lambdas that are essentially orthogonal to f. Okay, so definition which is due in fact to Sassvari, Berschneider, and maybe to somebody else. So X is F stationary if for all shifts H, the stochastic process H plus lambda, viewed as a stochastic process in lambda, has the same law of finite dimensional distributions as X of lambda. Okay, and what do you mean by H plus lambda? I take H and shift each one of the atoms involved in the definition of the measure lambda by H, translating the measure. Yeah.
Does one need to assume that this subset is a little large, not like very small?
You mean the F or the F lambda? Lambda F, right? Yeah. So all these lambdas that happen to kill every function F in this. But hopefully next slide will clarify it, right? So depends, I mean, what F is. If capital F is too big, you may have to use up all your, basically every, not too many lambdas are going to kill all these functions f, right? But so this is interesting, a curious fact that if you have a linear, keep things simple. So f is a linear space of continuous functions, r from R to the complex numbers, which is finite dimensional and invariant to shifts. So it turns out that f must be spanned by complex exponential polynomials. Okay. So that's a curious fact, and this fact basically Matheron mentioned in a sort of by passing, and it's proved in the book of Saswari. Motivates him to focus just on polynomials. So basically he ignored the complex exponential part. So if my class of trends f's is described by all polynomials of degree up to k, then we arrive at the notion of intrinsic stationarity, or intrinsic random function of order k is such a stochastic process x of t that this relation holds basically. If you index x by a shifted measure, t plus lambda, you get a stochastic process equal in law to the original stochastic process x of lambda. Okay. For all lambdas that annihilate polynomials, all lambdas that kill, I have a few examples to come, basically, but these lambdas are plenty. These are signed or complex measures that have zero moment, so to speak. Okay. Yeah. So some special cases just to include in our consideration the class of stationary processes. By convention we call IRF minus 1 the class of all stationary processes. But basically lambda minus 1 consists of all measures lambda, essentially. Lambda 0 is the class of all such signed measures that kill all constants, which is easy to come by, such types of measures, so on. But let's build some intuition of these on this language. So IRF 0 is the class of stationary increment processes. Why is that? If you define this particular measure mu t, which is a delta function at t minus a delta function at 0, certainly every such measure will kill the constants. Okay. But if you index your process by h plus mu t, this basically means I'm looking at the difference at t plus h minus th. So really, indexing the process by such types of measures amounts to differencing, essentially. And it's clear how this equality, so the intrinsic stationarity of order 0, would imply the classic notion of stationary increments. And the converse is also true. You can go higher order. So IRF k is essentially the class of all processes with k plus 1 order stationary increments. But what does this mean? This is fairly clear when d is equal to 1, when you're looking at process index by the real line. But in general, the formalism of Matheron allows you to actually work simply with these types of objects in arbitrary dimension. And one more example just to see how these things work. Okay, indeed, if you define lambda dx as basically this linear combination of plus minus binomial coefficient times a delta function of minus j going from 0 to k. This is nothing but essentially exactly the k plus 1 order differencing on the real line. Here we live on the real line. And in fact, you could do some math, and you see this is the kth convolution power of the measure nu, which is the simple difference of lag 1. Okay. And indeed, indexing any function f by lambda amounts integrating against this thing, which amounts to basically taking k plus 1 order increments. Right. So there is a bit of something to keep in mind. When I talk about IRF k, this corresponds to k plus 1 order increments, essentially. Yep. Yeah, go ahead.
Just because I'm seeing this for the first time. So,
yeah.
So you started with the stochastic process, which was indexed by RD, but you're visualizing as, like in this case, like indexed by the space of finitely complex measures.
That's right.
So why don't you start with like a stochastic process which is indexed by, like it's on omega across space of complex measures instead?
I could. I guess a simple answer would be then, I mean, you want to, if you have applications to geostatistics, or for example, the natural index is space and time, or space-time. So I guess that's my simple answer. But in principle, yeah, abstractly, on an abstract level, this is not anything new. Theory has been done by Gelfand and Vilenkin and exposed in a beautiful volume in the 1960s. So yeah. So, but if you want, so then it'd be interesting to see when, if you have a stochastic process indexed by, let's say, the Schwartz space of functions gives you a, has a real function that represents it, So that's right. So the mind shift is, yeah, as you said, we will be indexing the processes by C-valued measures. That's all. But can you go back? It turns out that you can go back. That's the beauty of Matheron's theory. So if I have a stochastic process indexed by these lambdas, you can find special lambda t's. They're really special, such that if I define a stochastic process indexed by t, call it x-eyebrow t, then it turns out that x of mu is equal to x-eyebrow of mu for every mu in lambda, in capital lambda. Okay. So in other words, you can go back between, and this x-eyebrow is called a representer, and what it really means is that essentially I have pinned the process at certain fixed points I've chosen. So this x-eyebrow is not unique. Again, the difference between x and x-eyebrow is if it happens that x is a process, real process defined by the Euclidean space. So the difference between two such things would be a polynomial trend. Yeah.
There should be a t in.
Oops. Yeah. There should be a t. No. Here there is no t. Sorry. Here there is no t. So what I'm trying to say is that, okay, imagine that as we were saying, if you have a stochastic process indexed by measures, can I realize it as a stochastic process indexed by time integrating against a set of measures? And I can, luckily, with this formalism of Matheron. So you just have to index them with suitable measures. And okay, this is really not complicated. It's kind of like interpolation tricks and stuff. But yeah. So some topological details which I'll skip in the interest of time. And this is a good way to hide things I don't understand. So, so basically, I mean, it gave us a lot of trouble how to prove some of these results. And we had to define carefully the topology of what it means for our stochastic processes to take values in to have continuous paths. But Matheron defines a certain topology, sort of convergence on the space of these measures, which works, but it didn't work for us. So anyways, let's bravely ignore that. Tangent fields and Falconer's theorems. So, oops. Yeah. So remember the big picture. We want to look at the local behavior of these stochastic processes, but our stochastic process take values in a Hilbert space. So fine. I mean, we'll have to somehow normalize increments of these stochastic processes. Well, how do you normalize objects in a Hilbert space? With an operator, perhaps. Has to be an operator. So we will call this a scaling action. So an action on this multiplicative group 0 infinity on the Hilbert space, which is continuous and has some nice properties, will be called a scaling action. And really borrowed the idea from the paper of Holt and Lidskog, who looked at regular variation of metric spaces. So these, there are 4 properties or 5 properties that this action has to satisfy. I'll just give you examples of actions. The usual scalar multiplication action, TA, is just rescaling x by a constant a. The linear operator action is a little more interesting. Well, both are interesting. Take an operator, curly h, on the Hilbert space, and look at its exponent. Rather, look at a to the power of h, defined as exponent of log a times h. And this is an action satisfies these properties that I'm not even not mentioning. If you impose certain conditions on its spectrum, the real parts of its spectrum have to be included in 0 infinity and something else. But the intuition basically is that if I take an x and I rescale it by this action, it should go to infinity in norm as a goes to infinity, and it should go down to 0 as a goes down to 0. And there should be some radial monotonicity. Okay, but these are technical things that we need for our notion of a tangent field. So here is a definition. We say that the stochastic process y, again taking values in the Hilbert space, is the tangent process of x if, when you look at x indexed by t0 plus r times lambda, where r is going to go to 0, under this scaling action, converges in distribution to a stochastic process. And this convergence in distribution is in a certain path space, okay, which I forgot to on purpose mention. But it could be in finite dimensional distributions as well. Okay. So what is the intuition behind it? Well, lambda plays the role of taking a difference. Where? Well, in a neighborhood of t0. Why in a neighborhood? Because r is going to go to 0. Okay. And so this, without the scaling, will likely vanish. So we end up rescaling it suitably. Okay. And CR, of course, it has to go to infinity. You know, you need to rescale it. Remember, our scaling action sort of works in a natural way. Okay. So it turns out that if a stochastic process, Hilbert space stochastic process, has a tangent process like this, which is non-zero, non-trivial, then the scaling action has to be such that this constant, okay, you see, there is this C of r is just a constant valued function of this amount r by which we rescale space-time. So it turns out that this C of r must be regularly varying with a positive regular varying exponent alpha. This is standard, okay. And of course it's self-similar in this case. This is also fairly standard in this fashion. So if you rescale the index of y, then you have to rescale the space of y with the corresponding scaling action. And again, everything is relative to a fixed scaling action. If you pick a different action, pick different rules of the game, you get different tangent processes, of course. So just an example that this works. So for k equals 0, we recover the classic notion relatively quickly. I mean, remember this mu t, which was just a delta function at t minus delta function at 0. Okay. This really realizes, this form on the right-hand side, x of t0 plus r mu t, realizes the natural notion of an increment that appears in tangent processes. Okay. So really, if we have tangent process in this fairly abstract kind of way, we recover the classic notion of tangent processes. Here's classic Falconer's theorems. So if you have the classic tangent process of a stochastic process, x, okay. Well, let me actually read this theorem more carefully. It's an important result. He wrote 2 papers, maybe 3, on the subject. And under varying assumptions here, I'm assuming that you have a stochastic process x that has continuous paths that are real valued. Okay. And look at the increments. Assume that this convergence holds in the space of continuous functions equipped with a topology of local uniform convergence and so on. And this happens for every s here. The tangent process exists at every s in a given interval, for example. Interval, okay, what's an interval? Okay, in a given space, in a given Borel set of RD. Okay, sorry. So naturally, the tangent process will have to be self-similar. But what's very fascinating is that almost all tangent processes will have to have stationary increments. And this is not obvious at all. And the almost all is not a technical assumption. It's not an assumption of convenience. There are certainly tangent processes that are not with stationary increments. And this has a result. It had some mysterious proof for me. We had to redo it, and we thought we had our own proof, but of course it turned out to be wrong. So we ended ended up using his lemma. So the key lemma was Lebesgue density, a lemma on Lebesgue density 1 sets. It's a fascinating result. I highly recommend it. But what's the message of this? You know, even if you look at the classic theory, that basically if you have a Gaussian process X, then locally it behaves like a process, a Gaussian process, of course, which has stationary increments and it's self-similar, so it's fractional Brownian motion. So almost everywhere, every Gaussian process is fractional Brownian motion. Of course, model the fact that tangent processes exist. So what motivated the beginning of our research is, well, does this phenomenon exist when X takes values in the Hilbert space, number one, and what happens in higher order with higher order increments? And yeah, the answer is essentially yes. So this is a result. Not stating any proofs. So assume that you have, again, similar story, but we're going to be indexing by lambdas that belong to measures that kill polynomials of order up to k. Okay, and we have this tangent process. Okay, as r goes to 0, we have convergence in distribution in a certain path space for every s in a certain Borel set B. Then for almost all s's, Lebesgue almost all s's in this Borel set, we have that the tangent process is not only self-similar but with intrinsically stationary. So stationarity of increments of order k essentially comes in, which in the language of Matheron means intrinsically stationary of order k, which means exactly that. Okay. So the intuition again is, so indeed Falconer's results extend. This is a general phenomenon to processes in taking values in the Hilbert space, and even in, to higher order increments if you have the right notion of stationarity. Okay. So this motivated us to look at more closely at, so what happens if we, with the spectral theory of intrinsic random functions. So intrinsic random functions are important because they realize almost everywhere. Not just, you know, they're not random things that arise almost everywhere. So a little bit of terminology. We have a bounded linear operator A from a Hilbert space to a Hilbert space, and this is a separable Hilbert space. The trace class operators are basically those, they're compact operators, so on and so forth, but basically they're singular values are summable. Or in other words, if you look at the adjoint times the adjoint of A times A, you get a positive self-adjoint operator. So the square root is defined. Take its square root. And well, the trace of a positive self-adjoint operator can be written in this fashion for every complete orthonormal system. So basically, the trace norm of an operator A is defined in this particular fashion. So operator is trace class if this is finite, and it doesn't depend on the choice of the basis, so on and so forth. This norm, the space of trace norm operators or nuclear, or something like that, is a Banach space. So if A is, of course, positive, we'll call it positive. It's self-adjoint, and of course, it's positive in this fashion. Okay. So the covariance operator, why do we bring this up? Because we will want to look at second-order theory for stochastic processes, which means taking cross covariances. Okay. So it turns out that if you have a random element in a Hilbert space with zero mean, okay, so its covariance is a trace class operator, positive trace class operator. Okay, so what do I mean by second order? When X and Y are random elements in the Hilbert space H, then, well, we call them second order if the expectation of the norm squared is finite. Okay, and we will be taking always zero mean stuff. So what is the cross covariance operator? It's basically the expectation of X outer Y. Here I defined what X outer Y is, but the best way for me to think about it is think of X and Y as vectors. That's the outer product. Okay. And that's the trace class operators are is a natural space to where the cross covariances take their values because yeah, and this expectation basically is taken in the sense of Bochner. Yeah, in the Banach space of trace class operators. All right. So let's have a stochastic process indexed by these lambdas, which is zero mean and second order, H-valued. So the cross-covariance operator function is simply basically a function of lambda and mu in this case, which is the cross-covariance between y of lambda and mu and y of mu. We know it's trace class. If lambda is equal to mu, this is of course also positive. And we will call this y second order process, second order IRFK. If it so happens it's covariance stationary, what does that mean? Well, this cross covariance doesn't depend on time essentially. So if I look at C of t plus lambda, t plus mu, this is C lambda comma mu. It's a little counterintuitive here because, okay, why do we have two things, lambda and mu? Okay, isn't it true that it should depend only on the lag? Well, it's true, it depends only on the lag. But somehow, so in fact, I could have more economically put a single lambda here because of the polarization identity. I can recover everything, but anyways, bear with me. So our goal is to understand the second order properties of the RFKs Y. I mean, what do we mean by that? Well, we want to basically characterize this covariance, stationary covariance functions. So if Y is L2 continuous, whatever this means, then Y is second order IRFK if and only if this covariance, cross-covariance operator function is just equal to a plain old function K evaluated at a special measure, lambda convolved with the reflected mu or mu tilde. I'll define this in a second. But basically, the way I read this is the cross covariance is essentially a function just of the lag. Okay. I don't know if I can convey more intuition. Where this K, okay, remember, somehow we need to reflect the IRFK property. This K is a continuous, conditionally positive, semi-definite function of order K. Okay, I will, that takes values in the space of trace class operators. I'll just describe this a little bit more detail. What do we mean by that? Well, lambda is some sign measure supported on some SIs. Mu is another measure supported on some TJs. Mu tilde is, if mu were real, is basically the reflection of mu, sort of mu of minus mu minus dot. So if you just work out the calculation, it's not nothing special. You could see that the convolution between lambda and mu tilde has atoms given by Si minus Tj, and the charge is Ci times Dj complex conjugate. Therefore, K evaluated at this convolution of lambda and mu tilde, which describes all possible covariances of second order RFKs, is just that. Okay. All right, what is the definition of a conditionally positive semi-definite order K? From textbooks in the 60s, a function is conditionally positive semi-definite order K if for all lambdas that belong to lambda K, this form, let's read the right-hand side, the sum over I and I prime, Ci prime complex conjugate of K Si minus S I prime is positive. And it's interesting, you know, this kind of condition appears in the definition of variograms or whatever in the properties of the variograms, which I'll mention in a few minutes. Okay. So we'll return to this characterization. But just to recap, every continuous conditionally positive semi-definite function yields a valid cross covariance. Okay. And this appears again in the 70s in the theory of Matheron. I guess we understood it more properly in the case when your stochastic process takes values in the Hilbert space. And K is called the generalized covariance function of your IRFK. All right, so this result extends the Matheron formula, which in some sense appears in a different notation essentially in Gelfand and Vilenkin's text, but basically describes all possible continuous conditionally positive semi-definite order, positive semi-definite functions of order k. That is, it describes all generalized covariances for IRFKs. And these are just functions taking values in the space of trace class operators, T. It has to be, unfortunately, because we're dealing with the Hilbert space valued things. And it's an integral that very much resembles a Levi-Khinchin formula, in fact. And it is exactly a Levi-Khinchin formula for k equals 0. So let me just describe the ingredients. You have the indicator of an arbitrary bounded neighborhood of 0, as you see in the Levi-Khinchin formula. This pk is a Taylor expansion of the complex exponential. And you have a correction factor in the denominator that appears in. Okay. So this whole beast is integrated against a finite measure chi that takes values in t plus, the positive trace class operators. Don't ask me about how these integrals are defined. I mean, it's fairly straightforward, I guess. So this is one term which one can think of coming from the Levi measure type term. And you have something that corresponds to, I would say, the Gaussian component type term, which is some polynomial q in H with coefficients, of course, in the space of trace class operators. And the degree of this polynomial is up to 2k plus 2. So these are details. Okay. So for reasons why trends don't matter for us, polynomial trends don't matter for us, q is only unique up to a polynomial of degree 2k plus 1. But the measure chi is uniquely determined. Okay. So this is a cumbersome formula. It's a little ugly. Let's write it in a different way. Hopefully it will make it a little more transparent. So remember that k, the importance of the generalized covariance is that every cross covariance of an IRFK process can be written as k of a measure of this type. Okay. But let's take a look at this measure. It's not difficult to see that the convolution of lambda and mu tilde will kill polynomials of degree up to 2k plus 2. No, 2k plus 1, sorry. 2k plus 1. It turns out, well, the Fourier transform, I have it in the following slide, I think, yeah, all right. So the Fourier transform of a convolution naturally simplifies to the product of the Fourier transforms. And of course, the Fourier transform of mu tilde is the complex conjugate of the Fourier transform. So the previous ugly formula, in terms of nu, when you index your generalized covariance by measure nu, which is this convolution, lambda plus mu, convolution with mu tilde, is simply like this. Okay. And I'm not going to go through the calculation. It's straightforward. Basically, this correction polynomial term ends up being annihilated by the measure nu. Okay. But here is the beautiful formula I wanted to convey. So the Fourier transform nu hat is just lambda hat times mu hat complex conjugate. So the cross covariance of y lambda y mu has this expression. Integral with respect to some measure which is nice. Basically, you can think of this integral in fact as a summation, if you will. Okay, nothing prohibits chi to be an atomic measure. This measure assigns positive trace class operators to every du. That's fine. It's finite. And these things here behave just like they should for this quantity on the left-hand side to be positive definite functions in lambda and mu. So kind of the formula makes sense. So great. It's not too difficult to see that you could have a Cramer-type stochastic representation, just like for stationary processes. So in other words, you can represent every L2 continuous IRFK with values in the Hilbert space with two components. One is a stochastic integral, okay, with respect to a measure with H-valued, Hilbert space valued, and orthogonal increments. And the other component is some sort of polynomial, which you cannot avoid in general. Okay. So, not going to dwell on this. I wanted to end with a break from abstraction. And actually, my time is running short. So this is pretty abstract, but I claimed it is quite useful because, you know, these results mean modulo natural assumption of L2 continuity characterize everything that could possibly happen with a second order structure of processes with higher order stationary increments taking values in a Hilbert space. And we have all kinds of beautiful uniqueness results. In a way, the second order structure is characterized by this generalized covariance, which in turn is characterized by a measure and a polynomial part. So a little break from abstraction. So forget about Hilbert space. Let's say our process takes values in a real line. And forget about higher order increments. Suppose that k is equal to 0. So we talk about stationary increment processes. And this is familiar to many of you in this audience better than me. So we will be working with the stationary increment processes. We'll suppose that they have 0 mean, they have finite variances, and let's say they start they're 0 at 0. Okay. So in this case, we know that the law of the process is characterized by the variogram. Sometimes people look at the semi-variograms. Okay. So because of the same old trick, you could take and express the covariance of yt and ys through variances of yt, variance of ys, and variance of the increment. So dating back to Schoenberg, so all possible continuous functions gamma that can be variograms have been characterized. They are negative definite. So this means that, just recalling, for arbitrary choice of cj's which add up to 0 and arbitrary t sub j's, this form, sum over cj ck complex conjugate gamma tj minus tk, is non-positive. Okay. But this really resembles the conditional positive semi-definite stuff. Why? Well, indeed, I mean, I claim that this immediately means that k, which is negative gamma, is conditionally positive semi-definite of order k equals 0. Well, why is that? Well, if you define this measure lambda in this fashion, just because these cj's add up to 0, they kill all constants. So the lambda belongs to lambda 0. And this form here appeared exactly in the definition of the notion of conditionally positive semi-definite of order 0. So really, our generalized covariance in this case is just negative the variogram. It so turns out. So for that reason, from the classic Gelfand-Vilenkin Matheron formula, we have an expression for gamma of t, which is basically in this fashion. All right. So this is very, very close to the Levi-Khinchin formula. In fact, it is exactly the Levi-Khinchin formula. But I want to clarify that connection for a few minutes. It's one of my favorite results, even though it's not new, it's well known. So if you have a continuous gamma from Rd to the positive line, so this gamma is a valid variogram if and only if it's the exponential or the negative exponential of a characteristic function with a symmetric and infinitely divisible random vector. Okay. So I'm just going to, because it's a break of form abstraction, I'm going to show that. So take a zero mean Gaussian process y with stationary increments and variogram 2 gamma. This is what it means. Okay. So then, because it's Gaussian, the expectation of e to the I, this difference, is just e to the negative, the variance over 2, which happens to be e to the negative gamma sj minus sk, on one hand. On the other hand, let's take and substitute this right-hand side in the formula that tries to prove positive semi-definiteness, so to speak. So because these here on the left-hand side are basically characteristic functions, it's not difficult to see that this expression here equals exactly the expectation of the absolute value of this sum over cj to the I x sj, absolute value squared. And that's non-negative. So this little argument shows that if you have a variogram, e to the negative gamma is a characteristic function. But if you have a variogram, c to the gamma is also a variogram. So basically, any positive power of phi is also a characteristic function. So it's infinitely divisible. So you have a Levi-Khinchian formula. And you can do the converse. I'm not going to do it. Basically, if you start with a symmetric infinitely divisible characteristic function, then its negative, its logarithm is a valid variogram. So by the Levi-Khinchian formula now, you have this expression of the log of the characteristic function. And by the uniqueness of this, of the two formulas coming from Matheron, coming from Levi-Khinchian, you see that these are one and the same quantity, basically. So there is an interesting correspondence. So if you have a stochastic process with stationary increments in second order, e to the negative its variogram is basically the characteristic function of a symmetric infinitely divisible random vector in RD. Has to be symmetric. Right, so there's a connection to stability, of course. So stability links naturally with self-similarity in this case. Okay. So what do I mean by self-similarity? Just to recall, y is H self-similar. If you rescale time by c, positive c, then this equals in distribution to the rescaling the process y in space by c to the h. Okay. So this immediately translates for second order processes into this type of homogeneity of the variogram. Okay. But if the variogram is homogeneous, and we know it's the logarithm, essentially negative the logarithm of a characteristic function, well, naturally you see that the variogram has this expression. So the variogram of H self-similar stationary increment random field in RD can be written in this fashion, which is the negative of the exponential of a characteristic function of a symmetric alpha stable random vector. Okay. And every choice of an angular measure or spectral measure sigma gives a valid variogram and so forth. So I find this fascinating. But of course, it's not new, perhaps, to you. It definitely was not new to Jim Quelbs, who did this in infinite dimensions. And he has a section in his paper written in the 70s. Right. All right. Of course, you can work with operators. Naturally, if you want to rescale time, space with an operator, with a linear operator action, you get an operator stable connection to operator stable laws, which Mark Benchard studied and Hilmin studied quite a lot. All right, so let's move on. I just want to finish with a few words. So this was a break from abstraction. Let's go back to self-similar H-valued intrinsic random functions. So the previous discussion of the second order characterization of intrinsic random functions did not assume any self-similarity. But we know that tangent fields are, in addition to being intrinsically random functions, namely stationary increments, they're also self-similar. Okay? So it's natural to take a look at this. Okay. So we will look at this in a kind of limited way, because remember, the self-similarity really hinges on the choice of the action. So you can choose a nonlinear action, you can choose something complicated. So we will just choose a very, very simple operator action. So our action is going to be c to the power of h. So we want to look at and try to understand the second order structure of intrinsic random functions that are self-similar in this fashion. So y of c times lambda is c to the power of h. H is an operator acting on y. Remember, y takes values in the Hilbert space. Okay. This I just want to demonstrate this. I don't even have a proof, but the proof is not even necessary. The success, sort of the power of this characterization dating back to Matheron. So when you have this representation, remember this comes from the characterization of the second order properties of y. So the cross covariance of y lambda and y mu can be written in this fashion. Okay. Where chi k, well, I rolled up in this measure the normalization here. So chi, remember, chi was a finite measure, which is unique. Here I added some density. Okay, whatever. So simple change of variables. And the uniqueness of chi allow me to immediately conclude that if y is self-similar, then this measure has this particular scaling property. So if I rescale the measure, remember chi is a measure that takes values in some strange space of positive trace class operators. So you rescale the argument of the measure chi. This is equivalent to rescaling it on the left and on the right in space by these operators c to the negative h and c to the negative h adjoint. So this kind of forms appear in the papers of Gustavo Didier and Valdes Pipires, who characterized the operator fractional Brownian motion 11 years ago. But in polar coordinates, just like anything that has such a scaling property, just like with the regular variation, you can write things in polar coordinates very conveniently. So if you introduce polar coordinates, it turns out that the measure chi corresponding to H self-similar IRF k looks like this. Looks like this. Basically an arbitrary finite t plus valued measure sigma on the unit sphere, sandwiched between r to the power of an operator and r to the power of operator adjoint times dr, whatever. Okay. So that's the general characterization. I see people are tired, so maybe I'll stop here, leave people a chance to ask questions. Yeah. I can keep going. Yeah.
So you have in the Falconer's theorem like the almost all S,
yep.
which you extended.
Yep,
but
yep.
I didn't see it later coming anywhere. Like, did it?
Oh,
does it cause any problem? Like,
no.
later part of the
No, no. Well, we didn't connect the dots essentially, but basically, I don't know where Falconer is. No, it's just a very physical thing that comes from Falconer, from Mother Nature, basically. So here, this result assumes that if you have tangent processes at every s in a given region, right? Okay, so these resulting family of tangent processes, almost all of them will be stationary increments. Almost all of them will be stationary increments. So there's some examples, pathological, very, very easily you can construct an example where a tangent process exists, but it doesn't have stationary increments. Of course, all tangent processes have to be self-similar, but not all of them have stationary increments. This doesn't cause problems later on because we just assume stationarity of the increments and want to and just focus on it and study it. But yeah. Yep.
Can some part of the theorem be taken outside of the Hilbert space?
I guess, yeah. So we worked with the linear vector space in these theorems. So yes, so actually in our paper the result is proved in a separable, in a Polish space with a linear structure. Yeah, but yeah. So the Hilbert space is essential when we talk about second order theory, I guess. Yeah. Yeah.
So this is a nice Polish space, this SC.
Yes, that's right. This was the topological details which I was trying to hide. So in our proof, our extension of the proof to Falconer, we needed basically our process to take values in a nice path space. And this path space had to be Polish, complete separable metric space. And it took us a lot of time, and we had a lot of trouble finding the right topology on the lambdas that induces, Polishness of the path space of x of lambda. And then we gave up, and we decided to basically induce continuous path property through the representer. So to be honest, this is just a technical nuisance. Yeah, but it's actually an essential one for the argument. Yeah. Yep.
At the beginning, you started with the general lambda.
That's right. In the big.
And then you move on to polynomials.
Yep. That's right.
So are there other lambdas?
I'm sorry. There are other type of intrinsic stationarity, or other than polynomials. Yeah. We haven't done much, but my single motivation behind looking at polynomials is this curious fact. So Matheron hasn't looked at even the complex exponentials. He just took polynomials, as far as I know. So even if you stick to a finite dimensional shift invariant space, maybe you can look at something that has complex exponentials, polynomials. I don't know. I don't know if looking at different classes F will change much.
When you say for some polynomials, it's
all polynomials, sorry. All polynomials of degree.
Up to some degree.
Up to degree less than or equal to k, yeah. Yeah, so this is what intrinsic random function means in the spatial statistics literature. But yeah, I mean, in fact, actually the results of Berschneider, I have to admit, all this was done under the guidance of these works of Sasfari. He has a very nice book, in Berschneider. They didn't, as far as I understand, look at Hilbert space valued processes, but yeah, but they've developed a more general theory of F stationarity. Yep.
In some way, if you take that theorem of the representation of the finite dimensional
Yep.
it will be interesting to get rid of the polynomials and just stick with complex exponentials.
Yep. Yep.
So then you get a kind of
Signs. Yeah, that would be very interesting.
So,
Yeah.
and the measures will be very different. Will no longer be the discrete measures, right?
That's right. That's right. But I guess the trends are not going to be going.
Right.
Maybe that's okay. That's okay. Yeah. That's right. Thanks. Yeah. Thank you. Thank you.
Thanks again.
Yeah.